you can integrate now our nanosensors in areas where conventional sensors don't fit. So you could think of, for example, a minimal invasive surgery instrument where you can't really fit a regular sensor, and there you can fit one of our nanosensors quite easily.
Digid are making microscale waves in the nanoscale sensing game, which makes those waves pretty big for those who know their metric prefixes. I have some questions, and I'm sure you do too, about how small these sensors really are, what you can sense with them, how you can interface with them, and where you might see them popping up into the future. To truly get to the bottom of this, allow me to introduce you to Dr. Malte Kuehl. Malte, thank you so much for joining us in this studio today. I have so many questions. The first one is, how small are your nanoscale sensors really? You know, we say nanoscale. Are we talking the nanometer level?
Well, if you can think of a human hair, it's kind of the hundredths of human hair in length. We can even shrink it down. So we really can customize it, and we claim that we likely have the smallest industrial sensor out there, yeah.
Likely the smallest industrial sensor in the world. Okay, the word sensor is great, but what can't you sense exactly?
So yeah, we can sense either temperature, pressure, or forces, so strains. And yeah, we can print these sensors on any custom material, like you can imagine, basically.
Okay, so you say you can print these on any surface, that's great, but why would you want to make a sensor this small? I mean, you know, when we're talking about temperature sensors, we can get down to the 1 by 1 millimeter sort of area. What is the purpose of going even smaller?
Especially if you want to integrate nanosensors into parts where they can't fit right now, you can integrate now our nanosensors in areas where conventional sensors don't fit. So you could think of, for example, a minimal invasive surgery instrument where you can't really fit a regular sensor, and there you can fit one of our nanosensors quite easily.
Amazing. Yeah, so what other applications? So you say surgical is a big application of this because, you know, if you have a pair of pliers is not the right word in a surgical sense, and you want to be sensing temperature, you don't want a component sticking out of your scissors. What other applications do you see of nanoscale sensors?
Exactly. So there are several applications in the medical field. Robotic surgery, force sensing on the robotic surgical instruments. It's a very huge topic. Nano-invasive surgery I talked about. The end effectors, the tip you're calling, make them smart, know how much force you act on, and how much temperature you're using is a very big topic. But also, yeah, temperature in for example, engines, for example, or electrical drives, where you have really tiny spaces. One area is also batteries. So the batteries have these small pouches, and you're basically sensing on top of the pouch or at the lead. And now you could basically also array over the whole area of the battery pouch, in every pouch you have in your battery pack.
Right. So, okay, let's go all the way back to basics so people can understand how this is working. How do you make these sensors? How do you make them this small?
Basically, we developed a printing process, which is we use a high energy beam and a precursor molecule, and the precursor molecule is cracked by this highly focused energy source. And that's how we print the sensor exactly where we want it, into very small sizes.
Right, so this isn't like a standard IC. You can physically print a structure onto an item, correct?
Exactly. So the thing how we do it is we structure the electrodes. So usually you need to connect the sensor somehow. So you have the structured electrodes, and over the gap of these two electrodes, plus and minus, you reprint the nanosensor itself. And if you have an array, you have multiple leads, multiple electrode gaps, and you can spread them across the area where you want to print it. Exactly.
Cool. So, okay, so we've got a very small sensor. We're saying up to 100th of the width of a human hair is the maximum length of this sensor. How do you interface with something like this? I mean, I cannot simply grab a soldering iron and go attaching. How do you interface with this, and what measurements do these sensors give out? Is it resistive, capacitive, I2C?
So depending on the application, we can do voltage or resistance. So it's a piezo resistor, the sensor itself. If we use a bridge configuration, obviously we can also read out voltages. And usually you integrate it as I said, we structure the electrodes on the material. So you can come with your custom material and we structure it to make the electrodes and the positions of the sensors. So we design that for you. And then we print the sensors, and then somewhere is a point of connection where we have, for example, leads or very, very small cables, like smallest wire gauges you can think of to fit the signal to the measurement device, ADC, or whatever is needed at the end. Yeah.
So the way I'm understanding this is you can't just go ahead and buy this sensor off DigiKey. For someone who's interested, how do they start developing with this? They can't just buy it and have it delivered.
Exactly. At the moment, we don't sell generic sensors on DigiKey or Mauser. So usually we start with a development project with the customers who have their material and their idea where to integrate one of our sensors. And we start with the prototyping phase or go with a mock-up. And from there on, we engineer our way to the final product. We have the capability to print these sensors in millions. So it's also really, really scalable. And we work with different customers from all different areas and industries to make their product smart or smarter and integrate a sensor where space is key.
Amazing. Doctor, thank you very much for joining us today.
Thanks. Have a good one.
That was great. If you want to hear more about Digid, we'll have some links down below that will surely help you out. And remember, stay disruptive.